Dear students, this is the seventh lecture we are going to do today. And in this module, we have completed 6 lectures so far in video. And last video, we discussed about the solubility of two metals or binary alloys. That means there are two elements in this alloy. Last week in the video, if you can watch it again, so you will be remember what we discussed last time. We discussed complete solubility of two material or two elements when we are melting it and when we are cooling it, how that happens. And today we are going to discuss two things, that is complete insolubility and partial solubility. Now when it comes to complete solubility, we know using three methods it can be soluble in the particular liquid, and it can be interstitial or substitutional or intermediate compounds. We discussed all three of them. Now we also discussed when it comes to the complete solubility, these two elements, when we are mixing them, they mix like water and sugar. Once they mixed, we can't see them separately. But it is completely different when it comes to complete insolubility. There, these two material we are going to put together as a liquid, they are not compatible with each other. They are not mixing with each other very well. So it's just like something we are putting water with sand. Even after hours of stirring, you will see sand grains separately and water separately. So something like that we are discussing this in this section, complete insolubility. So here in this graph, what you can see is we have A material, we have B material. It can be A metal, B metal, or sometimes B can be a non-metallic material. We know what is alloy. Now we have 100% A here and 100% B here. So along the axis, the composition changes. So in the middle, we have 50% A and 50% B. So hope you understand what this axis representing, the weight percentage of each element. So here we are discussing about only two elements, A and B. Now in this, here you can see the temperature axis. In this phase diagram, we consider or we assume the atmospheric pressure is 1 atm. Under 1 atm, we are doing this experiment and see how these two materials behave. Now we know if we take 100% A, when we are heating it, it will come to certain temperature. We call this as the melting temperature. Melting temperature of the material. When it comes to 100% B, this is the melting temperature of B. And remember, these are variables we are putting, or like expressions we are putting for elements. These are not exact elements. It can be ferrous and carbon, this can be zinc and lead, something like that. Now when we take this material both together and when we put it and heat it until they become a liquid, then we let it to cool itself. And when it solidifies, this is the graph you will see with respect to their composition. Now remember, this is not a one experiment. This is more than 100 experiment in a one graph. So let me explain. First you have to melt only A, so you will get this point. Then you have to melt this, you will get this point. Now you are putting 99% A and 1% B, so you will come to this point. And likewise you will getting each and every point by changing the composition of these two material. When you come to here, somewhere here, let's say somewhere here, you can assume that this is 25% A and 75% B. So this is the dot or the point you get. So connecting all these points, you will get this graph. I hope you understand. Now when you look at this phase diagram, this part should be the liquid, and when it comes down, it become partially solid, then it become solid, completely solid. Then we know from this side, when it is solidifying, liquid become still liquid, but when we are reducing the heat or cooling down, in this side A is high, right? In this section, because in this side A 100%, so in these regions A is very high. Because of that, A solidified first, because A is there in higher amounts. Because of that, again A solidified first, but liquid is still there. Still this is a high temperature. Then when we are cooling down again, right, it or normally happens, right, then it become A and B. In this side, the amount of B is high. Here 100% B in this side. So in this area, B is very high. Because of that, B solidified first. Then liquid is still there. Now once it solidified completely, A and B will be there. Now look at this. Not like earlier, when we draw the graph earlier, it was when we mix A and B, it become alpha or beta or whatever the Greek number we are putting there. But here, since they are insoluble, same thing will be ended up having the last minute. So here what happen is A and B will be remains, but the design or the structure can be quite different. But A and B is still there without interacting with each other. Because of that, A and B alloy will be there, right? It's still the alloy. It's a composite, right? So, but the thing is, it haven't mixed with each other. Because of that, A and B still we can see if you see through the microscope. So I will show it that later. And here something I have to clarify, right? We know that A and B is here, but remember that in each region of this graph, the composition of A and B is different. For when it comes to this side, A is very high. When it comes to this side, B is very high. Okay. Now here you will see something different than earlier. Here there's a point. I have named it as E, right? The speciality you will see in here is if you come along somewhere here, let's say line 1. If you come along the line 1, it is liquid, then it's become liquid and solid A, then it become A and B. Okay. So what happens here is, it's a normal way we see something solidified. And even if you put something, let's say you are putting ice, or no, you are putting liquid water in the fridge, right? But it will take some time it to become ice in the refrigerator, solid ice, right? So let's say it is a 1 hour, but in the meantime, if you open the fridge and see, you will see solid ice with water. Still water is there. So this is something like that. Solid will be there, still there is water. But after the 1 hour, you will see solid ice. Now, in this line, line 2, if you come along, the liquid, in a certain temperature, I have put it TE, it just, without a blink, it becomes solid. Liquid, within very short time, it becomes a solid A and B. Now, let me explain what these are. So this point I have named as E. I will explain what it is. And this is this temperature of E when it is happening. So I have put a line over there. And this is the composition when E happens. It can be, we don't know what is the composition. It depends on the materials we have. Let's say in this picture, we can get an idea. Let's say this is A 60%, B 40%, something like that. Right? This is just for you to get an idea. When it comes to line 3, it is just like the line 1 here. It will start as a solid, but B solidifies first and then A and B. Right. Remember, in this section B is high, in this section A is high, because composition of A and B in both sides they are different. Now let me explain about the point E. The name of this point E we are calling as a eutectic point. Eutectic point. That is a new word for you to learn. So at the point E along this line too, liquid become A and B within very short time. Such a transformation is known as the eutectic transformation, or we call eutectic reaction. Right? So there are more than 5 or 6 words like this: eutectic, eutectoid, peritectoid. Likewise, different reactions are there in this phase diagram. Right? So I will explain those things, and I will tell you a way to remember these things in an easy way. So bear with me for some time. Now this eutectic point we are calling eutectic point, and this is the eutectic composition, and this is the eutectic temperature. Right. Now take a paper and a pencil. So now we are going to draw these structures along the composition axis, and what happened along the temperature axis. Just like we did in last time, we have 3 lines, so we have 3 structures to draw. Remember, in this complete solubility, partial solubility, and this complete insolubility, there are different structures are forming when they are solidifying. Right? So always practice drawing these things, so it will be very easy for you to understand what is actually happening. And sometimes you may feel that it is quite difficult to understand, so you can always put a question in the question forum saying that I don't understand this particular part, so please explain it again. So I will mark those things, and I will come for you with those things in the revision once we start the university. All right. So first we are going to draw the microstructure along the line number 2 here. Right. For here, first it is liquid, then it's very short time, we call it in English Shanikava. Right. Here it's become A and B. Now we don't know actually what is the composition in here. Right. So you don't have to guess it. So we are going to learn it in questions. What are the actual composition when it comes to the actual element, right? Now, in here we know it is liquid, right? So please take a pencil and paper. Please do that. Otherwise, you won't be practicing these things. Right? I can't see you here, but when it comes to physical classes, you always have to draw these things. I will give you time to draw these things in the physical class. So, but here, since you are online, I can't see you. So I don't know what's happening in your end. Try to do those things. Right? Okay. So here we know it is liquid. So the structure we can put as liquid here. So here is just a graphical interpretation. What you can do is you can make a circle or draw a circle and put dotted lines here and there. So normally that's how we draw the liquids, right? Please, if you are asked in an assessment or during the exam to draw these things, please name what it is. Just don't draw it. After drawing it, put an arrow and let us know this is a liquid. Okay. Now, only there are 2 pictures here. So then, after the transformation, this is a very quick transformation. It become A and B. Now here it's a something tricky thing, but you need to have a closer look at this, right? If you look closely, you can see in the PDF I have uploaded here, there are lines here, right? I couldn't highlight these things very well, but you can see in these places there are lines here, right? In here even there are lines in different directions, right? This is how grains appear, and inside the one grain the metal is structured in a particular orientation, but in different grains the structure orientation is different, the direction is different. That's what make them grain boundaries. Okay. So here what happened is this A and B, I told that A and B is not mixing. But what happened is when it is solidifying in the eutectic point, right? This is only happening in the eutectic point. So let me show the maximized one right here. The black and white stripes are I have given to just for the notification. Okay. So what happened is when it's solidifying at this, say very quickly, what happened is A and B just like laminates, right? A and B lamina structure will be formed, right? For this structure, it is called lamellar structure. So please write it down. This is not mentioned in this particular slides, right? This sandwich type structure of A and B likewise, this is called the lamellar structure. Lamellar structure, L-A-M-A-L-L-A, lamellar structure. It's like a laminate, right? Or sandwich we can call. So in different directions, this lamellar structure will be formed along this eutectic point. In other lines, it is quite different. I will tell. Right? In this points only, the lamellar structure will be formed. So please draw this. Take some time, pause the video for some time, draw this your own. Okay, hope you have done that. This is the actual image of that eutectic structure. Here you can see lamellar structure of A and B. So this is I think martensite structure of steel, most probably. And here we can see A and B, A, B likewise. So this is called a lamellar structure. So in actual case, this is how you can see it, right? This is not 100% perfect, but this is how it happens. Now, this is quite little tricky. Drawing line 1, line 2. And remember, line 1 and line 2 you will see the same thing happens, but here what happen is in line 1 amount of A is high, right? Here amount of A is high along the line 1. In line 2 amount of B is high. So when you're drawing this, I have put in a different perspective, right? So we don't know what are the color of AB, but for our argument's sake or our lecture's sake, let's say I have put A in light color, B in gray color. So even in the lamellar structure, we saw white and black. So that is just for our understanding, right? That color happens because of different thing. Because when you see from the microscope, there will be light beam putting on top of the surface. The reflection we are getting into our eyes through the lenses in a microscope. So we don't know how these the light is reflecting from the surface. So light is an amazing thing when it comes to the microscope. So you will understand if you are doing something ahead when you are doing the NDT as well as in higher studies. So light scattering is a different thing, right? So I'm not going to talk about it right now, but if you can remember me, put a reminder during a physical lecture, I will explain something different about light as well. Now, along the line 1, how we are going to draw the structure. First, in this point, we know this is a liquid. So we can draw the liquid part. Then L and A occurs, right? So here there's no lamellar structure like earlier, just only A occurs here. So I have colored A in black, right? So now this happens because this area or this composition is high in A. Because of that, A will appear first. Now B is not appearing right now. B will appear after passing this eutectic temperature only. And remember, inside this liquid, right? This is important. Inside this liquid, A is still there, right? A and B still there. The reason A solidify first because A is high in this region, but still extra A is still in this liquid. So when you come together, A and B is still there. Now what happened is, so this happened in this region. So A will occur in this region. Once it passed the eutectic temperature, with a very short time, this A and B in this liquid will form the earlier structure in the eutectic one. So this is we call pro-eutectic A because it happens before that. Now here what happened is the pro-eutectic A will be there, then the liquid become this crystal structure I have mentioned earlier, the eutectic crystal structure, lamellar structure happens here. So here you can see in the grains there are lines again, right? These are A and B lamellar structure, but the A occur earlier is still there, right? Now what happened is, so the A is there, no? So the earlier this pro-eutectic A is there, but there are no, so this is still inside the A and B grain. Now it is solidified, but what happened is this pro-eutectic A will be pushed inside the structure. Pro-eutectic A will be pushed into the grain boundaries, telling that A and B will be there. A, you go to the grain boundary line. So what happened actually is this pro-eutectic A will be squeezed into the grain boundaries, or the, let's say in Sinhala we put them aside, a corner. So right? This is we call putting aside the earlier one to a corner, and A and B lamellar structure will be the domaining part in here. Hope you understand. Right. So this is a structure along the line 1, and if you draw the structure in line 2, same thing happens, but what you can do is change the color a little bit, then same thing you can draw. So I will show you that as well. So pause the video, try to draw this your own. Okay. So microstructure changes along the line 3. It's quite same like earlier. Liquid first, then what occurs here? Since this is rich in B, this side is rich in B, B solidifies first in this region. So we call pro-eutectic B. Then still the liquid contain A and B. And this A and B, once it passes this line, it will become A and B lamellar structure like earlier. Then this pro-eutectic B will be squeezed into the grain corner, and it will be shown like this. This is what happens, the composition along the line 3, if the composition is somewhere here. Now remember, this is not one experiment again, right? This is not a one experiment, this is a collection of hundreds of experiments along this line. So we can change the composition one by one and draw the microstructure, right? So I'm not going to go into that depth with the time we have, but you will understand what I am talking about here. So try to draw this, right? Try to draw this. Then you will be able to decide what happens in a very short time when you see these phase diagrams. These are very simple phase diagrams. These things will be not in the actual environment. I will show you what are the actual phase diagrams in a little bit. All right. So with that, we end this one. Last one we did what it called complete insolubility. Now we are coming to the next one, partial solubility. Partial solubility. So what happens here? In complete solubility, it's like water and sugar, they mix together very well. We can't see what it is there. In complete insolubility, it's like water and sand, when they mix together, even after hours, we will see sand and water separately. It's just an expression, not the actual thing. When it comes to partial solubility, what happens is, in the graph you can see A high in this region, B high in this region. Now what happened in here is, in the A high region, if you put little amount of B, it will be completely soluble. Okay, hope you understand what I'm saying. I'm telling you again, in the A high region, A is higher in here 100%, so it's, let's say, come to this point, this is 99% A. When you put B 1%, it will be soluble. Okay, it will be soluble. So in the line in here, you can see, just like the first line we discussed, come here, then it become alpha, not A and B. Since this is soluble, it become alpha, right? And remember, though I telling it is alpha, it always doesn't have to be alpha. Okay, this is an expression. This is just an Greek letter I have put into this particular one. You can put beta, gamma, delta, whatever the name you want, right? For our case, I have just put alpha because that is the way I feel about these things. So and this is mostly the norm. Yes, samane wenne ehema. All right. So here alpha occurs, and also in this region we know B is high. B is 100%. If you take this line here, this dot here, it is 99% B and 1% A. And if you collect A and B here, it become not A and B like earlier, it become beta. Here it's become beta. So it dissolve with each other very well. Alright. In the middle, what happen is, alpha and beta will form, but this alpha and beta is not much compatible. Now remember, alpha mean high A, low B. Beta mean high B, low A. These are different structures, two different structures, but they are not compatible together. So by mixing, they don't form gamma or something else. It's just alpha and beta like A and B, right? I don't know whether it's tricky to understand. Basically, what happens, right? So here the liquid will be there, and here alpha occurs, solid alpha, and in between here liquid and alpha. Here beta, this is liquid and alpha, and that become alpha. Here liquid and beta. And just like the complete insolubility, along this line, liquid within very short time become A and B. No, it become alpha and beta. So this is the phase diagram when it comes to a partially soluble two metals or materials. Partially soluble, not completely, partially. Bargetter. Now we are going to draw the microstructure when they are mixing together. And here still there is a eutectic point. Hope you can see. Liquid become alpha and beta very quick time. So it is still a eutectic point. And if we go along this line, you will see eutectic temperature somewhere here. Right, somewhere here, the eutectic temperature. And this will be the eutectic composition of A and B. Now, how we can draw this? So, if you have draw the earlier two, this is nothing. It's very easy to draw. So, let me show the lines 1, 2, 3, 4, 5, 6, 7. Okay. Though it's 7 structures, right? They are the mirror images. So, if we take the line 4 as a mirror, 1, 2, 3 is a mirror image of 5, 6, 7. Just the color will be changed. Same thing happens, color will be changed. But in actual cases, these are two different materials. But in this example, or the expression of the phase diagram is very easy. Now, if you look at these three lines, so here you will still see liquid become alpha and liquid, this then become alpha. So here it is quite easy. This is what we did earlier, complete solubility. And line 2 is quite tricky. Here liquid become liquid and alpha, and then all become alpha. Then out of nowhere beta appears. And I will show in the phase diagram when it comes to the structure. And line number 3 is a line we did in the earlier one, which is complete insolubility, liquid and become liquid and alpha, then alpha and beta lamellar structure. Here alpha and beta lamellar structure. Hope you understand. Now let's see how we can draw these things. 1 you can draw very easy, 3 you can draw very easy, 4 you can draw very easy, and same when it comes to this side, 5 and 7 you can draw very easily, that you have learned in earlier 2 stages. But 2 and 6 is quite tricky, but they are the same. Okay. Now, microstructural change along the line 4, that is the middle line, the eutectic line. We know liquid within a very short time become alpha and beta. Since alpha and beta are not compatible, they will make alpha and beta lamellar structure. Okay, alpha and beta lamellar structure. Hope you can see these lines. In a normal presentation in the class, a normal student can't see these lines, right? In the PDF I sent you, you can see that, right? It is quite hard to see, but remember this is the reason for this is the poor graphic skill of my end, right? If I'm good at drawing these things, I will draw it very sharply, right? So please, sorry, beg your pardon for that. Right. In the next line, line number 3. So we did it earlier as well, right? In complete insolubility, we did this. Liquid is there, then alpha appears, right? Inside the liquid, alpha appears, and we know inside this in liquid, alpha and beta is still there, extra alpha and beta. Then they will make a lamellar structure, and the pro-eutectic alpha will be squeezed into the corners of the structure. Here there is no A and B, this is alpha and beta, and I explained what is alpha and beta earlier. I will do it again. Alpha mean high A and low B mixed together very well. Beta mean high B, low A mixed together very well, completely soluble. But alpha and beta not good at meeting with each other, so they become alpha and beta lamellar structure. Now, when it comes to the next line, so here the mirror image of the 1, 3 here. So I have put it in different color, you understand what it is actually. So here, same thing, line 5 and line 3, the mirror images, only difference is alpha and beta, differences are there. Along the line 1, we know complete solubility. So this is how we draw it in earlier case, complete solubility in the earlier video. Liquid become alpha and beta in this side, here alpha and liquid here, then it's become only alpha, right? And you may have a question here. The reason is, even only alpha here, there is B here. Since alpha in higher quantities, B is soluble in this A and B, so only alpha can be drawn here, no beta here. But something happens in this line, that is the line number 2. Okay. Here. So what's happened here? So it will seems quite not clear here, but let me show you, right? So let me come with the line 6. The same thing in another way. In this liquid, so liquid is first. So there are 4 circles there. First it is liquid. in here, okay, then it's become liquid and beta, then it's become totally beta here, that is this structure, totally beta here. Then out of nowhere alpha appears. The reason is, in this liquid still alpha is there, but it hidden inside the whatever the let's say different void spaces in the solid, and they will come together in this temperature. They will collect it in the corners and show their cells. That what happens in here. This is a rare occasion actually. This doesn't happen normally in many cases. So I hope you understand what this line actually represents, right? So first B in this side, what happened is here same thing. Liquid, first it is liquid, then liquid and alpha appears, and it makes the whole or let's say the full soluble or complete soluble structure here, and out of nowhere the beta occurs. Beta which was inside the structure, and they like right? So from everywhere the structured or the beta will come and gather in the corner of the grains. So that is how in partial solubility how we draw this graph. So sometimes it will be quite difficult to understand the line 6 and line 2. So please remind me during a revision lecture. I will do that again. So you will get more, you can get clarified about how this is happening. So please remind me on that. And if you have any question, I will put a question forum. You always can, you always can ask your questions there. Even they are related to this lecture, or if you have any question regarding to coming into the university on 5th, right? If you have watched this video, if you have any question regarding to that as well, you can ask. Because in an actual lecture, you and I will be sitting facing each other. So you have, whatever the question you have, you can shoot me. You can shoot the question to me. I can answer. So not only the questions regarding to this lecture, if you have any question regarding to the university related matters, so since you are coming in on this October 5th, if you have any related question, you can always ask. Just put in the question forum. I will try my best to answer those things as well. Okay, with that I'm going to stop recording this video here, and I'll start the next video from the next slide. So see you on the next video with a short break.